Alright, so I'm going to record a video for binary logistic regression. The lecture in class didn't work out right, so we're re-recording this on my computer. And so to just kind of go over what is log regression before we get started, the idea behind logistic regression is that it's a non-parametric design. So non-parametric statistics do not require the same assumptions as parametric. So with parametric statistics, your ANOVA, regression, t-tests, correlation, it requires that you have at least the DVB scale, so at least ratio or interval, and then normality, linearity, and so the assumptions we've been going through this entire series of videos. But each one of those has a non-parametric companion that doesn't require the DVB scale. If it is, that's great. It'll convert it to a ordinal or a nominal scale. But it also does not require the assumptions. So when you can't meet the assumptions of a parametric statistic, you can do a non-parametric version. With log, very specifically, the DV or the outcome variable is categorical. So the point of this analysis is to predict some sort of group membership. And so it's kind of if you have two groups, a t-test on its side. The parametric version of this is called discriminant analysis. But you have more power with the logistic regression when the assumptions aren't met. And sometimes it's really hard to meet the assumptions unless you have huge samples. And with huge samples, they end up being about the same. So personally, I always do log. Discriminant has its place, but if you can understand a log regression, then you're kind of covered. Okay. So we're using a mix of categorical or continuous IVs to predict a binary DV. Or in this particular case, the other video that's on YouTube, I have a multinomial log regression where I have more than two outcomes. So some quick definitions. I still have my predictor variables that can be any combination of different types of things. So I can do categorical, continuous, Likert scales. They don't have to be normally distributed at all, which is great because that sometimes is a hard assumption to meet. I would say linearity is probably the more difficult assumption. Your DV has to be your group classification or group membership variable. So what happens is in a regular regression equation, we're trying to predict someone's score, y hat, given the intercept for y, or the mean of y, and then multiply that by a weight, make this a little bigger, for each x variable. So the slope, or unstandardized slope, ends up being how much for each increase in x, how much does y increase. With a logistic regression, we're predicting group membership, y hat, but using a log odds formula of it. So we're taking the log of u. Well, what is u? U is the regression equation here. So I have that written here. So we're basically calculating the slope values, but then taking the odds of it to create the predicted group outcome. So what happens when we get our fitted values or our predicted or y hat values is we're getting the log odds of one person and being in group one over the other group. So you always have to know which group is coded as the control or the baseline group so that you know how it's predicting, because you're always getting the odds of the second group. And so if the odds of the second group are low, that means they're probably in the first group. If the odds of the second group are high, they're in the second group. Traditionally in a binomial, or binary, log regression, you're going to use a 50-50 cutoff, which is sort of a median split, which isn't the best idea, but it does force group membership into one or the other. But you are getting the log odds of, or the odds ratio anyway, of the second group. So there are a couple of different types of log. I only covered two of these in my class. So binary log is what we're doing right now. Multinomials where you have three or more outcomes. And then there are subtypes of each of those. So a direct logistic regression is the same thing as a simultaneous regression. You just kind of throw all the predictors at the wall and see what sticks. A sequential or hierarchical log regression is where you code the variables in steps. and then you look at model change from one step to the next. A statistical log regression is, now I'm in psychology, usually used as sort of a screener, or when you don't really have any theory. So this isn't super common because we are a theory-based science, and we tend to really focus on that. And so when you try to say, well, I just ran all these variables and here's what happened, people sort of criticize that as like not good science. Probit is sort of a halfway point between log and a regular regression. And so probit is kind of somewhere in the middle. It has the assumption the DV is normally distributed, but that it is not totally continuous. So it's sort of an in-between log and regression. Now for power, there are ways to do power, but because we like things to be nice and simple around here, what we're going to do, and we'll do this in here in a second, is run this the same as a regular regression. So log will have more power in a regular regression when the assumptions for regression aren't met, which clearly you won't have a continuous DV. And so you can just kind of estimate from G power and get a good number of subjects to run. There are other ways to do this, but they get really complicated really fast, so I'm going to show you the easiest way. Because this is a non-parametric test, the assumptions are totally different, which is cool because there's less of them. So you do have to have a categorical DV. The more groups you have, the more difficult this becomes. So I really recommend keeping it on the lower end. You do have to have a large N in each group. So think about it this way. If I'm trying to predict people who go into group 1 and they go in group 2. Well, if you have a 80-20 split where everybody's in group 2, you'll get it mostly right if you put everybody in group 2. So having to predict a small category is very difficult, sometimes nearly impossible. So if you have a bunch of small categories, maybe collapse them together, collect more data if that's possible. But it's really difficult when there's a lopsided ratio of cases. And so this happened just last week with a student I was working with who was testing this selection procedure. So they had, maybe 40 people in one group and 180 in the other. And I was like, that's not going to work because you'll get it mostly right. Your prediction will look like you're doing well because if you just predict that everybody's in the big group, you're getting it mostly right. So one thing that you can try is randomly sample from the larger group and make the two categories equal to the smaller group. I test that a couple of times with a random sample to see how well your prediction's doing. If you throw everybody in there, it's not going to work. So you always want more participants than IVs. Log, sometimes people just use lots of variables just to see what happens, and so make sure you always have more participants than IVs. Additivity, we still want predictors to be separate things, otherwise we're wasting our time. So we want to make sure our predictors are not too correlated. And then this last one is something you just have to know is true. So independence of errors, I can only be in one group. So this particular analysis does not allow for repeated measures. We are predicting which group you go into. You cannot be in both groups. If you have some people that are sort of a both, make that a separate category. So you can have 1, 2, or both. But that would be a multinomial log, which is not what we're doing here. If you watch my regression videos, I like to talk about with regression as, does the model predict? Right, and then in this particular case, the question becomes, are we predicting group membership better than chance? And this is really a question of, is R squared greater than 0? And so to do that, from the output we're going to look at a null model, which is a model with no predictors, versus a residual or a fitted model. It says residual on the output, which is a little weird because it says residual error, so it's error, but a fitted model that does include predictors, and compare them. Regular regression runs this way, but it just gives you the F-test and you don't think about it that way. But in this particular set of output, we're going to see null model, residual model, and you want the error to be smaller on the fitted model. Okay. So it's going to show you the error term, and you want the error to be smaller, which is kind of backwards the way we think about it. We normally think we want our fitted model to be better, but a better model has less error. Next thing we'll look at is the individual predictors. So if the model is significant, great, but what about the individual predictors? So this is technically a walled test. It's going to say Z on the output, but it's basically testing if B, or if we convert these to log odds or beta, are those different than 0? So are they helping us predict? And it's a type of chi-square. We are predicting odds of group membership, so positive predictors increase the odds of the group coded second. Negative predictors decrease the odds of the group coded second, or just the vice versa. They increase the odds of the group coded first. So this isn't like as this goes up, this other one goes up. It's as the odds ratio or the odds go up, the probability of group 2 goes up. For effect sizes, there's a bunch. I had always learned that Nagelkirk was one of the best ones, but McFadden, there's a bunch more. There's two of the most popular ones are Cox and Snell. So it's an R squared based on those likelihoods and the sample size. But it's been criticized that it can never reach 1, even if you get everybody right, which only happens in made-up data, right? The Nagelkirk R squared is an adjustment to Cox and Snell so that you could actually achieve perfect fit, in a sense. There are a bunch more, but we're going to use Nagelkirk in this example, and that's in the Baylor Ed Psych package. Now, if you are going to do a multinomial log, and I talked about this more in my other video, you basically get 2 equations. It comes out in the output as one like giant equation thing, but really what's happening is you get predictors for the group coded as the control group versus the first group, the group coded as the control group versus the second group, and so you never really get 1 versus 2. So if you want 1 versus 2, you have to recode. And there are ways to code it as 0 to 1 and 1 to 2. But basically, everything's compared to kind of a control. So you'll get as many equations as you have levels minus 1. So if I have 5 different categories, you'll get 4 equations. So let's work an example of a binary logistic. If you're interested in multinomial, I have a different video up for that one. All right. So the question is, can we correctly predict working and non-working individuals by their attitudes and their demographics? This is a data set from the Tabachnik and Fidel. So our DV is work status. They're either working or they're not. Our IVs, couple of categorical ones: children, yes, no; race, white or other. Locus of control is continuous. That's internal, external locus of control. Attitudes towards marriage, attitudes towards the role of women, where the attitude, the higher the score, the more traditional the attitude, so barefoot in the kitchen. Socioeconomic status, attitudes towards housework, age, and education as a mildly continuous variable. So for power, like I said, we're going to do a traditional regression. So this is going to be F-test. And then linear multiple regression. Although I know it's not linear, just go with me here. Deviation from 0. I'm going to click determine and use a medium effect size for R squared. Oops, wrong thing. Alpha is 0.05, power is 0.8. The number of predictors I believe we have is 9 in this example. So I need 167 people. That's just a good guess. In a perfect world, those would be evenly balanced, where we had about 80 in each group. But that's just a kind of a quick way to estimate how many do I need without getting into anything super complicated. Okay, so I'm going to flip over to RStudio here. I'm going to load up my data set. So I'm going to look at the accuracy of the data, mainly just to make sure that everything looks correct. So we're going to have some trouble with these 2 variables. Now the ratio of cases doesn't necessarily matter for predictors, but it will help if you don't have small n, because then it will be a little easier to tell what's going on. these is heavily imbalanced. So it would be better if they weren't, but you can't really control this part sometimes. None of these variables should be negative. So they're all looking good. And then here's the good thing. We're not using this marriage variable. This here is a fairly even ratio of cases. So that's good for us. So we just want to look and make sure that the contiguous IVs don't exceed their min and max values. Any categorical variables are dummy coded or are set as factors in R, so it will dummy code them for you. Our categorical variables shouldn't have small or empty categories. I don't have any missing data, and at this point I really couldn't estimate it, so skipping that step. For additivity here, look at my correlations, my symbols for numbers chart, and it looks pretty good. So we just don't want anything where there are commas, where that means 0.7. Remember at 0.7 you start to get suppression issues, and at 0.9 you start to really have multicollinearity. So it looks pretty good because we don't have any commas or up. Alright, so let's try running this, and I'll just explain this as I go. So we're going to use the GLM function for generalized linear model. We're predicting work status with all of these variables. So I just put them on separate lines so I could see it better. Now this would actually run linear regression until we get to this line. This is where the logistic part happens. So it's saying use a binomial distribution instead of normal. The default is Gaussian, which is a normal distribution. And we're going to use the logit function. And then my data set name. I'm going to run that and save it as model here. And then give me a summary of that model. Alright, so we get some stuff up here at the front, at the top, and then mainly I'm interested in the stuff down here at the bottom. Okay, let me flip back here. So is the overall model significant? Well, before, with a regular regression, you just look for F, you look for your p-value, and it's just right there. However, here we've got this null deviance versus residual deviance thing. Good news is our error, because this number here is chi-square, its error, is smaller in the residual model, or the fitted model. But how do I tell if that's significantly smaller? This is very similar to what you would do in a structural equation model. So the first thing you want to do is figure out the chi-square difference. So I'm here. And because I saved this model, I can run this code. As long as you save it as model, it will be, the code will work. But what it's doing is it's taking 643 minus 587. Okay. I'm finding out the difference in chi-square, so the reduction in error by adding the predictors. But I have to have something to compare against, so we're going to use the chi-square distribution. So I've got my degrees of freedom difference here. So 464 minus 455, that's 9 for our 9 predictors. And then this function here, p chi-square, will tell me what's the p-value for that. So what is the p-value for this chi-square difference with that amount of degrees of freedom? And the logic of this idea is that we want to see if the change in error is significantly less than if we didn't have any predictors. So by adding these predictors, are we doing better, which means the error is less. So we're figuring out the change scores and then calculating p for those change scores. I got that all set up here. Turn off my scientific notation because otherwise you get e values, so chi-square difference, oops, degrees of freedom difference. My chi-square is 5517, so I want to report that with 9 degrees of freedom. P-value for that is very small. So yes, the overall model is significant. If I wanted to get my effect size for this model, since we've talked about effect sizes a lot this year, you'll want to install the Baylor EdSci library. And then the code's very easy. Sudo r squared of our model, so that's why we saved this thing. And then bam, it gives you a whole bunch. McFadden, Coxnell, here's Nagelkirk, 0.15, and a couple of others. So these are all very useful. So I would report that, I did the final thing here, as chi-square with 9 degrees of freedom, 55, p less 0.01, and then tell people which r squared you're using. Since there are a bunch of them, don't just call it r squared. If I use this as my R-squared, that's a medium effect size. So the next thing I did to understand the predictors or the coefficients is I first ran a table just to see which one was coded as the lower group. And not working is our lower group, our control. Working is our upper group. I could have switched those. If I flip them, what's going to happen is all the predictors will change signs. So it doesn't really matter. It just for interpretation purposes, you want to know which one is the lower and which one's the higher. And so the next thing I did was make a table. So I'm a not working group over here. Any predictor that's negative is going to go over here on the left side. Any predictor that's positive and significant is going to go over here on the right side. So let's scroll up here and look at this. So I'm ignoring the intercept. But for children, this is for the yes group, it's negative predictor. So that means it goes into the not working category. So if you have children, you're more likely to be in the not working group or less likely to be in the working group. So the people who don't have children are more likely to be in the working group, since this is a simple 2x2. Okay. So since it's negative, it goes into the lower group, right, because it's negative. And you use the, for dummy coded variables, the thing that's coded out here. So yes versus no, more likely yes for the not working group. For race here, the same interpretation. White folks are less likely to be working, so they're in the not working group. Locus of control and attitude towards marriage are both non-significant. Attitude towards the roles of women is significant, and it's for the not working group. So the more traditional your attitudes are, the more likely you're not to be working, which makes sense, you're at home. Socioeconomic status, so the higher the socioeconomic status, the more likely you are to be not working because you don't have to. Attitudes towards housework, not significant. Age, older folks are more likely to be working. This one's positive, so it's for the working group. And the more education you have, the more likely you are to be working. So don't think about these as sort of scary interpretation-wise. I love tables, if you haven't gotten that already. So I made myself a table and anytime it was negative, I put it over here for not working. Anytime it was positive, I put it over here to be working. So as age increases, you're more likely to be working. As ed increases, working, but then the converse for these over here. So people who have kids are not working. Whites are less likely to work. As traditional roles of women go up, less likely to work. Income goes up, less likely to work. All right, so now that we've interpreted those predictors, really we want to know, like, how many people did we get correct? One second, let me turn that back on. Okay. I know that some of my predictors are significant, my model is significant, but am I getting one group better than the other? And that, so far, we haven't gotten to. What sometimes people do is they'll split the data sets in half and then actually use it to predict the next, like the second half of the data. But it's just as easy to look at what you got correct in this portion. So both options are equally good. And normally we'll take those fitted values and we'll be able to just see how close we are to y hat. So if I have my predicted score, how close am I to my actual score? But in this particular case, if you look at what your predicted scores are, they're actually continuous because it's a continuous probability of being in the working group. So what we have to do if we want to understand how they would have been classified is convert that to a binary variable. I used a 50-50 cut point. That is just because I have two groups and that would be chance. You can actually change that if you have a theory. And so what I did was I used the if-else function, and it basically says if your correct variable is above 0.5, put them in the working group 1. If it's not, put them in the not working group. This is very similar to Excel's if function. So think here, this 51%, that's really close, but they're going to get classified as the working group. And then for our 45%, that's also pretty close, but they're going to get classified as not working. Oh, so here's an even closer one, 0.49. So anybody in that range right around 50-50 is kind of a crapshoot. It's just a guess because you don't have enough evidence to really classify them strongly in one group or another. So I'm going to convert that. All I did here was convert that variable to a factored variable, so the next step would be a little easier. Then I made a table of the original variable by my guess. So what this table tells me, I can make it a little bigger here, is for the not working group, here's the original variable, here's my predicted variable, and then here's how many people I got right. For the working group, and here's how many people I got right. So I want these two to be big, here and here, and then the off ones to be small, because I guessed wrong in these cases. What most people do is create a marginal probability. So marginal probabilities are the likelihood of this box given that row only, not the overall likelihood of it being correct. So these won't add up. So this is the probability of getting it right for just the not working group, and then getting it right for just the working group. So it's a percent match, so here, over the total for that row. So I calculated those out here, just hard-coded them. So the first group I got 60% right for the not working. I got 67% right for the working group. And then if you want the total percent correct, it's actually just the average of those two, but it's the percent match over the total. So it's 64-ish% correct. Okay, so those are marginal probabilities. That's the likelihood of the getting not working right, ignoring working, getting working right, ignoring not working, and then the probability of getting everything right. The other thing I added, because we did this for a poster and it just came out really cool, and I think you wouldn't necessarily publish this sort of thing, but visually it gives you a really good picture of like how well you did, is this kind of dot plot. So did this in ggplot, and I think ggplot has done something updatey, so my axis lines no longer print out. So let me fix it. I figured out the fix recently. There we go. So I have this theme coding that I've been talking about off and on throughout my videos of that just takes away all the hideous, ugly background stuff. So beyond that, what am I doing? Well, I've created a data set, a plot, a histogram. This is the original data set. I'm going to use my continuous version of my correct variable. So the x-axis is a continuous version of correct. So it runs from 0 to 1. It's the probability of group 2. And I'm going to split the dots by work stat. So I did color. You have to do color and fill to get this graph. Okay. So what's happening is this variable is our fitted values in a continuous probability, which is why I saved them as a different thing up here. And then this is color them by group. So the next line down adds our theme. geom.plot adds the dots. Position equals jitter is actually kind of important. So what that does is it keeps the dots from overlapping completely, so you can see the dots when they're on top of each other. I did chord Cartesian just to make x be 0 and 1, just to put the limits on it. Xlab is sort of like every predictor. What is my predicted score? Ylab is frequency, but that's a real misnomer, and I'll talk about why in a second. And then I made it pretty. So I colored them maroon and like steel gray, because we did this for a poster and our school colors are maroon. And then I labeled them so the dots are not working and working, and then gave the legend a label. And I did the exact same thing for fill, because you have to do color and fill or you'll get two different legends. And then the last thing I did was add a 50-50 line on the graph so you could see where we had split our cut point. So what happens here, make this a little bigger, is it's a frequency chart, and it's supposed to be a histogram. So normally you would get bars, but we changed those to dots, so each one of these dots is a person. The jitter keeps them from overlapping completely, so the space between dots here is just so they don't overlap. So it's not like this dot is somehow higher than these other dots down here. It's a frequency chart. So really they should be like stacked up, neat, cute little dots, but that's not easy to do. So the jitter just keeps them from, so I can see them. Here's our 50-50 line. So yeah, frequency, not the best label out here, but really what you want to look for is sort of ignore Y and look at where the dot is on X. And so all these black dots over here, they're very easy to classify. They're so clearly this working category. Okay. This red dot over here is on the wrong side. So all of our red dots should be over here. All of our black dots should be over here. And so everybody right here, you know, crapshoot. It's hard to guess where they're going to be. So these are sometimes called outliers in the solution, where the dots are really, really on the wrong side. So kind of in the bottom quartile here, these black dots, I might want to look at them and figure out, why are they being classified so wrong? Like, what is the variable that's really pushing them the other way and we're incorrect? And the same thing up here. So this just gives you a visual of how they sort of fell out, and you can kind of see if you have some people that are really classified incorrectly. Plus, it took me a long time to make this graph, and I'm very proud of it. So I just wanted to show other people. And then this was just a test of something else. Okay. And so that is how I would look at a binary logistic regression. The help guide here on our website has like all the code and the explanation, with the word explanation misspelled still. Let me fix that bad boy, of what's happening, and then an example of how you would write one of these up.